Hello everyone. In this week, we will discuss about classification problems and various machine learning methods for classification. In this week, I will introduce some basic ideas of classification problems. Also, I will introduce the concepts of some various machine learning methods for classification, such as logistic regression, linear discriminant analysis, and support vector machine. And finally, so you will have a chance to apply those classification methods in R. Okay, so a classification problem is to find the function for discrete outcome without an order. Remind that regression problem is for a continuous outcome variable. Discrete outcome variables are like gender or disease subtype or categories. Importantly, they should not have an order. Red, green, and blue, they are discrete and they have no order. However, low, middle, high, they seem to be discrete, but they have an order. Here, we only consider discrete values without an order. Some people may think we can use a regression method for classifications. It may be possible for binary outcomes. However, it's not obvious for outcomes with more than 2 levels. If the outcome is either cat or dog, we may encode cat as a 0 and dog as a 1. Actually, you can use any other number for this the encoding. Definitely, there's no fundamental difference. However, if there's the more than 2 levels, like 3 levels, it's not that obvious. For example, if we encode 1 for cat and 2 for dog and 3 for horse, it means that a dog is larger than a cat and horse is also larger than a dog in any sense, in whatever sense. You know this doesn't make sense. This encoding also means that the difference between dog and cat is equal to the difference between dog and horse. It doesn't make sense neither. So we like to apply a method dedicated to the classification problems. In the classification problem, the output variable y is a category or class of a sample. So fitting the class of a sample itself is not easy to be expressed mathematically. Instead, in many classification methods, try to model the probability of a certain class. In other words, it wants to model the probability that the class y is equal to k given that input variable x with certain function of x. Then the class of the sample y hat is estimated that actually as a k that maximize this probability. Here, okay, so the mean square error of a regression is given by 1 over n of the y minus y hat square. In the classification problem, the MSE is measured by an error rate, which is 1 over n times sum of indicator function that whether this yi is equal to or is different from the estimated class. Even though this MSE is calculated by an error rate, this error rate is not always used for the performance measure. There are more performance measures such as the specificity, false positive rate, and many others. Among various classification methods, let's start from logistic regression. Logistic regression is often applied for the classification of the binary problems, binary outcomes. Let's consider either y is 0 or 1. Then let's define the small px is the probability that y is equal to 1 given x. Definitely, the probability that y is equal to 0 given x is equal to 1 minus p of x. Okay? So here, we're gonna model this the p of x. Because the people like the linear model, as you know, we can model this p of x with a simple linear model like a beta 0 plus a beta 1 x. However, this linear model has a problem because by changing of this value of x, this linear model can be negative. But it doesn't make sense because it's a probability. So, in order to make it non-negative, we may want to use the exponent form instead of just linear function. So, we may want to model this px with e to the beta 0 plus beta 1x. Then this one is strictly non-negative. However, it still has a problem because it can be larger than 1, right? So finally, px should be modeled by in this way. Px is equal to e to the beta 0 plus beta 1x over 1 plus e to the beta 0 plus beta 1x. So with this form, we can, in this case, this px is strictly between 0 and 1. If this the denominator is very large, because this exponent is large, then this px becomes close to 1. If it is very negatively large or negatively small, then this term e to the beta 0 plus beta 1x is close to 0. Then this px itself is also close to 0. Okay? Then this px is between 0 and 1. So equivalently, this relation can be written like with this formula. Log of px over 1 minus px is equal to beta 0 plus beta 1x. This term is called logit of px. So basically, this logistic regression is we actually linearly model this logit of px with this simple linear model. So that's why this is the logistic regression. This is the typical plot of the logistic regression. First, there are observed samples like this. Okay? If x is small, y is more likely to be class 0. Okay? And if x is large, then it is more likely to be class 1. This is y equal 1, this is y equal 0 side. Okay? If we draw the logistic regression line, which is the sum shown in the previous one, this one, okay, then it shows this something like this kind of the S-shaped curve. When x is small, this value of this curve is getting close to the 0 side. As x increases, initially there is not much difference, but at certain the threshold, it actually increases rapidly. Then it saturated at 1. So when even though x is very large, this value is still 1. So we call this the S-shaped curve sigmoid function. if this, the x is very small or very large, the classification is easy. However, if x is around this transition point, it is a bit difficult to confidently say the predicted class. Since we have a model of the logistic regression, the next task is finding the parameter or coefficient. This here, in this case, beta 0 and beta 1. Usually, the coefficients are obtained by minimizing mean square error. This is the least square approach. For the sample of class K, the predicted probability to be class K is ideally should be close to 1. So, in this case, the MSE of the probability can be written by 1 minus estimated probability to be K. Okay? So, in the least square case, this MSE can be defined in this way. So, we want to minimize this equation. It is the possible approach. However, practically, the calculation of this the MSE minimization is not that easy. So instead of this least square approach, many people like to use the other approach, which is the maximum likelihood approach. Likelihood can be defined as the probability to observe the currently observed data under a certain model. For example, in this logistic regression case, the probability to see a sample with class 0 is given as 1 over 1 plus e to the beta 0 plus beta 1 x. And the probability to see a sample with class 1 is given as like this. Since all samples are considered to be independent and identically distributed, the probability to observe all of the n samples together can be calculated by multiplication of such a probability. So this whole probability is actually means the probability that we see these observed samples actually. Okay. The basic idea of maximum likelihood is that we see these the current samples because the probability to see these current samples are so large. So we want to find the model parameters that maximize this likelihood. In terms of actual calculation, maximum likelihood is a bit better than because by taking the log of this L, instead of using this L as it is, by taking a log of this L, we can make all multiplication as to be linear additions. Okay? Actually, the calculation of the logistic regression, maximum likelihood is more preferred. Okay, so in generally, we have the multiple input variables. So in the multivariate logistic regression, we just model this logit of the px with multiple linear regression like this. That it is equivalent to this one if you do some do mathematics. So px is given in this form. Okay, so this is the LDA. No. This is a logistic regression. Then let's move to the LDA, linear discriminant analysis. LDA is based on a bit different idea. LDA assumes that the samples of the class K are generated from a distribution with PDF of Fk. Different classes have different PDF functions, and the samples of different classes are generated differently. Also, LDA assumes that classes have a natural probability to be observed more. This is a prior probability that often noted by pi k. Finally, the probability to observe a sample of class K is proportional to the proportional to this prior probability times this its own PDF function. So when the observed data X is given, the probability that the sample to have class K is modeled by pi k and f k of X. But by itself, this is not the probability itself. So in order to make it as a probability, because we have the multiple classes, so we normalized by all of the possible cases. So we observe, so we model it with pi k times the fk of X divided by making sum over all classes of this pi l times the fl of X. Okay, so this is a model. This actually models the probability that this sample has a class K given X is a small x. So we call this probability is posterior probability. This is the very general formula for posterior probability. Here PDF of fk can be any probability. This one PDF of fk can be any probability distribution. Here LDA assumes normal distribution, specifically assumes normal distribution for this f. Each class has different mean, but they have all the same variance. So the PDF of each class is given by like this: 1 over 2 pi of the sigma. This is a common sigma, and expect e to the exponent of minus 1 over 2 sigma square times x minus mu k square. This mu k is class specific mean. Then this is the PDF. Then the posterior probability is given by like this, by multiplying this prior probability with this PDF divided by sum of these terms over all class 1 to large K. So this is a modeling of the LDA. Then LDA assigns the class of which pk of X is the largest, or in other way to say is the discriminant function is the largest. To compare this in the p of X, we realize that the denominator of the p, in this case, we want to compare this in the p of X, but we shortly realize that this, the denominator is common for all classes, so we don't have to care about this denominator. And also, among this numerator, 1 over square root of the 2 pi sigma, it is also common, so we don't have to care about this. Only what you need to care is pi k and exponent of this term. So then another point is find out the largest pk is equivalent to find out the log of the largest one among after log transformation. So if we make the log transformation, it become by ignoring this one and this term, it become this one become log pi k minus 1 over 2 sigma square. Then if we expand it, x square minus 2 mu kx plus mu k square, like this, then this one is equal to log pi k minus x square over 2 sigma plus mu k x over sigma square minus mu k square over 2 sigma square. Okay, but here also this term sigma x square term is also common for all class. So class index is k. Keep in mind that. So only this term and this term and this term is important. So that's why discriminant function is given in this way. Okay. So here, so if you look at this discriminant function of x, it is a linear function according to x. So that's why we call this method linear discriminant analysis. Here is an example. Let's consider two-class classification with k equal 2. The prior probability are assumed to equal as 0.5. Then we need to compare two discriminant functions. So in this case, delta 1 of x is equal to x times mu1 over sigma square minus mu1 square and 2 sigma square plus log 0.5 and the discriminant function of the second class is given by x times mu2 sigma square minus mu2 square over 2 sigma square plus log 0.5. So then the decision boundary should be the point that this discriminant function and discriminant function have the same point. The point that these two discriminant function has the same value. So then if we solve out this equation according to the x, then we finally reach the result that mu1 plus mu2 over 2. This is a decision boundary point, which is around 0 in this case. Okay. Then the question is how we can estimate the parameters. This LDA has the parameters. If we have the k classes, we have to estimate its prior pi 1 to pi k and their own mean point mu1 to mu k and variance sigma. In total, 2k plus 1 parameters. As we discussed before, we may want to use least square or the maximum likelihood approach to find out this parameter. However, more simple approach also works. First, mean of each class distribution is simply estimated by the sample mean of the samples of each class. So this is just a sample mean, I of which class is k. All right. Here nk is number of samples of that class k. And this the variance. This common variance is estimated as the within class variance. Within class variance. As you see here, we first measure the deviation of each sample from its own class mean. The square of the deviations are summed and divided by n minus k. Why n minus k instead of n? It is the similar reason that we use n minus 1 for sample variance that you have discussed in the statistics part of the previous course. Briefly, dividing n minus k makes this variance estimation has the expectation equal to the true variance. Anyway, then we want to estimate the prior probability. So prior probability is simply obtained according to the number of the observed samples. Okay, so I will stop here for this first session. We will keep going in the next video. Thank you very much.